everyone. My name is Liam Dougherty, and this summer I'm working with Professor Dr. Batra in the Department of Physics at Alabama A&M University. And my research subject this summer is the development of multifunctional, smart, flexible nanocomposites for biomedical applications. So, the way I'm structuring today's talk is I'm first going to talk about the motivation behind our research. That is why we're investigating the materials we are. Secondly, I'm going to introduce some important terms that will help everyone here understand better what I'm talking about. Then I'm going to go into the methodology, that is the way we're going to be doing experiments. And finally, I'm going to talk about the plan for this summer research. So, start off. As to technology is advancing, and there's something called the Internet of Things, where a lot of different small devices are going to be incorporating sensors. And as that field starts to emerge more, there's a growing demand for small and flexible sensing devices. And some of the desirable features that we want are low cost, lightweight, flexibility, and desirable figures of merit. And those figures of merit include high detectivity and high voltage responsivity. In addition to the applications listed here, these types of sensors are extremely useful in biomedical application. For instance, prosthetic hands. And that all is related to also artificial skin, because for a robot that's going to be doing potentially surgical operations, you want it to have a similar sense of touch that we do. And in addition, it can some other applications would be monitoring blood flow and measuring spinal fluid pressure. And some more desired features are we want reduced size and high spatial resolution. So, what are the important variables we want to measure in one of these sensors? Is, well, to start off, it's the dielectric constant, which many of you might already know. The pyroelectric coefficient, the piezoelectric coefficient, and the piezoresistive coefficient. And I'm going to go into more detail in a minute about what those are and why they're important. So to start off, one of the effect we really want is the piezoelectric effect. And the piezoelectric effect is the idea that certain materials, when applied to mechanical stress, generate the charge, the dipoles inside the material themselves become aligned in different ways and create a voltage or an electric field. And with a voltage and electric field, you get a current. Essentially, you're turning some of that mechanical energy of compressing the material into an electrical potential, which you can use to measure things or sense different types of applied pressures. Derived from the piezoelectric effect is the pyroelectric effect, and as the name implies, it has to do with heat or temperature. You want a changing temperature. Certain materials, when the temperature is changing, will also have the molecular structure will align a little bit differently, and that will create a temporary voltage. And you need a changing temperature though, and with the changing temperature, you get you get an electric field. You can drive charge, and that can be used to sense different things. And we're looking for the pyroelectric coefficient, and the coefficient is defined as the current that you get out of the material divided by the area of the sample times the rate of change in temperature with respect to time. Finally, we have the piezoresistive effect, and this is materials that exhibit the piezoresistive effect are already in application currently. It's very important because what happens here is, again, when piezo has to do with a pressure applied, and when you apply a pressure to the material, you get a changed resistance, and therefore, if you apply a voltage to that material, you get a different current. It can be used for different sensing applications. But unlike the pyroelectric and piezoelectric effect, piezoresistive effect does not produce a voltage or an electric field. So you're not going to get any energy out of the system that you apply the stress to. Okay, so the process that we're going to undertake to develop these materials with those properties that I just listed is going to be, first we're going to start off with PVDF, which is, as I have written down here, it's a complicated polymer material. It is known as polyvinylidene fluoride, and it's a polymer-based material. And what we're going to do is we're going to mix that material with nanoparticles, just small particles that are of a certain material that are going to help the material exhibit those properties. And so what we're going to do is we're going to mix them together, which is pretty much explained by the first 4 arrows there. And then eventually, once we mix them together and create a thin layer, what we're going to do is we're going to do something called pulling. And that's because in the material, naturally, once you've mixed everything together, the dipole moments are misaligned. But then when you apply to a strong electric field to the material over a long period of time, the dipoles align, and you have that pulling effect when you apply stress to the material. And after we've gotten to this point, we're going to move on to testing materials. Okay, so before we can start measuring more important piezo, pyro, and piezoresistive effects, we need to measure more basic electrical properties such as the dielectric constant, and we're going to be doing that with this machine here and a program that's going to read the capacitance of the device or the material, and we're going to be placing the material in this chamber here, which is going to be alternating the temperature, changing the temperature, and every time we move up a series of degrees Celsius, we're going to take another measurement to determine what has changed in the material. Then, so there's 2 parts of the dielectric constant. There's the real and the imaginary part. The real part represents the regular dielectric constant you think of when you talk about a capacitor. The imaginary part represents a dissipation factor, where you're going to be losing some of the energy or the heat. Heat's going to be dissipated, and we're going to measure this imaginary part too. It's important for the calculations. Another thing we want to measure is the gauge factor. The gauge factor, I mentioned it a few slides back, it has to do with the resistance, the changing resistance. That's all you need to know about that. We're using this device where we have a cantilever, and we place the material on the cantilever, and as the cantilever bends, the material is placed under stress, and we measure the resistance of the material through here, and we measure changing resistance as we apply a little more stress. So we're going to twist that, apply a little more bending to the cantilever, and then we're going to measure the resistance. Okay. All right. So those are so far the experimental procedures we've lined out in our department. More is to come, but currently the plan is that I familiarize myself with more of the literature. My professor has already provided many papers for me to read, so I am trying to digest those to my best ability. They're not, so I have a lot of catching up to do. And then I need to familiarize myself with the instrumentation and theory. So I need to, become all that equipment that I showed you. I don't know quite how to use yet, so I need to practice with that. And finally, familiarize myself with the experimental procedures. And hopefully by that time, maybe by the end of the program, maybe I'll come up with something novel or something to help them out. Like maybe just find a mistake in the, and like last year I did something similar to this, different REU, and what I didn't come up with anything new, but I did come up with a lot of ways to, a lot of bad ways of doing the experimental process, so they know not what to do next time. So whatever is going to happen, hopefully I'll do something. But that's it for me. Thank you.